about the motion of a falling object. The purpose of this lab is to construct models of falling objects to compare to an actual falling object. One of these models will include just the force of gravity, and the other will include the force of gravity and the force of drag. The process for this lab is to analyze the motion of a falling object in Tracker, identify the forces acting on the system, account for those forces in the GlowScript code, and then compare the models from GlowScript to the actual motion of the falling object. Finally, we'll explain why and how those forces change the distance versus time graphs. The main findings for this lab were that the model that accounts for the force of gravity is very similar to the observed model. The slope increases as time passes, indicating an acceleration and a non-zero net force. This is explained by Newton's second law. Unlike the first lab where we had a net force of 0, this lab has a net force because of the force of gravity and the force of drag. So we can use Newton's second law to update the ball's velocity and then use that to update the ball's position. For the force of gravity, we'll be using negative m times g, where g is just the constant 9.8 meters per second, and that reflects the force of, or the gravity between the Earth and the ball. Next, we'll use the drag effect, and that is found by using the proportionality constant and the speed of the ball squared, and that will be acting in the direction opposite to motion. Here's my experiment setup. So I used a hollow ball of mass 0.084 kilograms and dropped it from a height of 0.94 meters. I scaled the video using the bookshelf and made my time frame 0.4 seconds, which was just after I released the ball and before the ball hit the ground. I oriented the motion in the negative x direction and found the initial and final velocities using the change in distance divided by the change in time over the first two time frames. Here's a screenshot of my tracker output that shows the motion of the ball as well as all the data points. And then on the right is the output of my GlowScript code, which I'll discuss in just a minute. Later I did add vector arrows to show the force of gravity and the force of drag. So for my code, I updated the ball's mass, the initial position and velocity from my first data point in Tracker, and then I updated line 44, j hat, to reflect the axis orientation I had in Tracker. And then for my while loop, I made it the time span of my Tracker video and used the negative m times g formula to get my fnet. For the code with gravity and drag, I found the proportionality constant by finding the b constant where my last data point aligned with my actual ball's motion. And then in line 58 and 59, I found the speed of the ball squared and multiplied that times my b value to get my drag force and added that to my fnet vector that already included my force of gravity. Here's my resulting graph. So specifically, the Tracker data starts initially from almost rest, and then the velocity increases as it falls. The model with the gravity was a very similar result, but it was slightly slower, and that could have been caused by an initial acceleration from when I dropped the ball. I could have added an extra force to it. And then the model with drag and gravity isn't quite as accurate, so that indicates that my drag force must have been pretty small on my ball. But other errors could have been, like I said, an initial acceleration, and then there was also air from the ceiling vent in the negative x direction or negative y direction, which could have accelerated the ball even further. So the terminal velocity is a constant speed where there are no forces to change acceleration. This means that the velocity will be constant and have a straight slope. So the model that shows gravity and drag would be the best example to find terminal velocity because it accounts for all the forces, at least in this closed system example. And then the next question was what would happen if your initial velocity was greater. And in line 35, I initially set my velocity to negative 0.509, and that's the blue line. And then I doubled that number and got the equation with the orange line. So if velocity increases, then the terminal velocity will also increase. So in conclusion, the model that accounts for the force of gravity is very similar to the observed motion. The slope increases as time passes, indicating an acceleration and a non-zero net force. And potential errors for this lab were an initial acceleration or outside forces such as an air vent that acted on the system.